So now in this video we're going to look at the NOT gate, the Schmitt trigger, which is added to the NOT gate. NOT gate could also be called inverter, a digital inverter, not a power inverter. And the 7400 series 14 integrated circuit. So 7414, this is the high-speed CMOS version. So that is the transistors, indicating the transistors in there. The different types of transistors, so different letters, will give you different electrical limitations, but they have the same basic property as far as the circuits are concerned. There's 6, hex is for 6, NOT gates in there. A is for input, Y is for output. First, for the physical demonstration, we got a lot to cover in this video. We have a low input right here. The trim pot is set to a lower voltage. It's closer to ground. You can see we got the red LED. It's light up. It's wired, to light up when the output is high. If I raise the voltage of the trim pot more than about halfway, it's actually not a specific voltage, but higher than about halfway, closer to the positive supply, or 1, the blue LED lights up. The output went low. It's close to ground. You can see the other side there is positive. And we have a middle ground, that's hysteresis. So you can see there's not one specific spot where when I jiggle it, the output flips high and low. It shifts slightly to kind of help lock it into the output so that you have to put a little effort to switch it the other way, just to prevent the rapid fluctuations of a wavering signal. With a 2-channel oscilloscope, you can see those voltages. So the trim pot's low, so that is channel 1. You can see we can wiggle it around. It's 5 volts at the power supply. We're not outputting 5 volts, but in case we raise the voltage of the input high enough, close enough to 5 volts, there is 5 up there, and you can see the output goes low. So low enough input, high output, high enough input, low output. Now there is a middle ground region right when it switches. There you go. We can go up a little bit before it switches again. So this middle ground region is called hysteresis. That is when you have a Schmitt trigger, you get that hysteresis. So now we're going to come back to the diagram. So the integrated circuit we have here, if you look, you'll see a part number that includes, there's also like other letters and stuff, but the main thing is it's a 7400 series integrated circuit. You'll see that number. High-speed CMOS, that's the type of transistors inside. But this is the number 14. So this is where you have the variations of what's on the integrated circuit. If it's 14, part of the 7400 series integrated circuit, it's a hex. There's 6 of them for hex. Schmitt trigger, we already talked about the Schmitt trigger. You can see the symbol there. That's added to the, it's a buffer with a little dot to make a NOT gate. So buffer takes the signal in and outputs that signal, but then the little inverter there switches it. So in any case, Schmitt trigger, inverters there, and inverters are the same as NOT gate. They're digital inverters, not power inverters, which take DC and output AC. Make sure you got that distinction. So in any case, we have also the NOT gate truth table. So there's only one input and there's only 2 states. So we have a high input close to 5 volts for this integrated circuit, and that output's close to 0 volts, ground. We just saw that. And a low input close to 0 volts. It outputs a high state close to 5 volts. Pretty straightforward. So now we have the integrated circuit here. We need to power it. So positive supply up there and negative supply, ground. So VCC is commonly used to indicate positive supply in circuits, and ground is typically used to indicate the negative supply when it's a single supply. The A's for all of these are the inputs. We have inputs that we're not using the output for anything, so it actually isn't terrible if you leave them floating, but it's best to put a voltage to the inputs. And I accidentally put the voltage to the output there when I was wiring this up. I should have turned the power off, but hopefully I didn't do any damage. These do have some protection, but you can fry these. I've fried some before, so should wire up with the power off. Now we're using the number 1 up there. So the input is on top, as it is with all the other ones. You can see it's coming across to the trim pot. We got the positive supply on one side, negative on the other. You can see I falsely triggered it, and we must be in that hysteresis range where it'll stay in whatever state it was last put into. But in any case, So coming to the middle pin of the trim pot, that's where I hooked that oscilloscope probe to, and our wiper slides across the resistive element closer to positive or closer to negative, giving us a fraction of the supply voltage. I have at the output, so that's getting our input voltage. At the output, 2 LEDs to indicate polarity. So the blue LED, you can see positive supply up there with the higher value resistor because it gets brighter with the same amount of current as a red LED. So we're limiting the current quite a bit through the blue LED. So they're about equal brightness, as you can see there. So it's connected to the positive supply long lead anode. That's anode up there, long lead, short lead cathode down there. Connected to the output. And actually we got the order reversed, but it doesn't matter the order as long as the LED is in the right direction. So that's to the output. And also connected to the output, red LED, again, resistors coming before the LED, but long lead anode up top, headed to the output, short lead cathode, going to ground, lower value resistor. So you can kind of visualize, right now blue LED is lit up. This is where the power ultimately comes from, and it heads that way. So on the schematic you can kind of visualize that too. Sometimes they have the supply pins on there, and it's going through transistors though, and it's providing current to a load, so it's not going to be completely 5 volts. It'll go up a bit if we remove the load, but usually they don't get 5 volts anyways. These integrated circuits though commonly go to ground really well, but again, it probably didn't. We probably saw it lifted a little bit when it was almost at 0 volts on the oscilloscope, because we have a load. If we remove the load, it probably would connect to ground directly. We could have done that, but I didn't think to do that. So, in any case, close to 0 volts blue LED, and close to 5 volts red LED. Hopefully that makes sense, and we should be done with that. So the high-speed CMOS version, that is what is commonly used now. If you look at like old equipment, good chance you're going to see LS for low power Schottky, and it's just not as effective as the high-speed CMOS version. They put in better transistors, and so like we have a range of voltage now instead of basically having to use 5 volts, and we can output and input about 25 milliamps of current, either sinking or sourcing, depending on whether the blue LED is lit or the red LED, but you want to limit the total current to 50 milliamps. So if you got more than 2 of them going, you don't want all of them sinking or sourcing 25 milliamps of current. And it's best not to leave the inputs floating. So you can look at the data sheet for the particular integrated circuit you're using, but generally they say don't leave them floating. Either tie them to positive or negative. So, in any case, that's it. Long video, so hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.